Okay, today we are discussing today's class. We will distinguish between open loop and closed loop control system. So two control systems we have. So let us distinguish them. Let us see what's the difference between the two, and then we will move ahead. So first we will consider open loop. Sorry, open loop. Then we'll consider here a closed loop. Okay. Okay. First point in this is first point in open loop is construction and design are simple and hence less expensive. So in this, construction and design are simple. So simple construction is there, no feedback, nothing else. So which makes it less expensive. So we don't need economically less expensive. This is one thing. In this case, it has a complicated design and more expensive because there will be lots of instrumentation in the feedback. So that makes it a complicated design, more expensive. Okay. Second point is generally stability is not a problem in this case because we don't have a sophisticated system, highly sophisticated system. So stability will be never a problem in open loop control system. It's not a problem in this system. Okay. So design should be we have to designer should carefully design what this closed loop control system as what will happen because there is always a tendency for this system to become less stable. So designers should be careful because it's complicated system and there will be always tendency to become less stable. That's quite normal. More instrumentation we have, more abnormality will come in the system. Designers should be careful as there is tendency for less stability. Okay, this is another thing. Point number third is less accurate and less reliable. Less accurate and less reliable. That's quite normal. Accuracy is less and reliability will be related to that. We don't have, this is not a highly reliable system. Just a second. Okay, so accuracy is less, reliability is also less. Highly accurate and more reliable. That's quite normal in this case. Because feedback is there. We are getting a signal from the feedback that compares it with the actual output and sends it to the error detector, and then the controller will take an appropriate action. Highly accurate, and more reliable. More reliable. That's quite normal in this case. Next is no feedback, output has no effect on input. No feedback. Output has output has no effect on input. So in this case, we don't have feedback in open loop control system. So output has no control over the input. Feedback is present. Output affects input. Feedback is present. Output affects input. It's quite normal in this case. Next is sensitive to the disturbance and environmental changes. Sensitive to the disturbance and environmental changes. And in this case, almost insensitive to both. Okay, next is small, it has a very small bandwidth, whereas bandwidth is larger bandwidth. Next is no non-linearities affect the response. So operation of the bandwidth will be smaller because we don't have a feedback and sophisticated system, whereas other the bandwidth will be larger. Non-linearities, that means any sort of non-linearity can exist in the system, that will definitely affect the. But if a non-linearity effect will be almost negligible. So effect of non-linearities is not to greater extent, to not affect the response of the system. Effect of non-linearities is not, it's almost negligible, not to greater extent. That means influence of the non-linearities, any set of non-linearities which will occur in the system will not have influence on the response of the system. Transient and steady state error cannot be controlled conveniently. Transient and steady state error cannot be controlled conveniently. Easily they cannot be controlled. Okay, just a second. Oh, okay. Transient and steady state errors. While any system is in operation, we have a transient state, we have a steady state. Error which will exist there, we cannot control those conveniently and with less flexibility. And it's also not flexible and with less flexibility. That means system is not flexible in open loop control system. Similarly, if we talk about transient and steady state errors can be controlled more conveniently. Transient and steady state errors can be controlled more can be controlled more conveniently, okay, and with greater flexibility. That means you can manipulate the system, you can look at the feedback, you can see the feedback signal, you can nullify that difference between the two. That's the greater flexibility, because you have lots of instrumentation in the feedback with a greater flexibility in closed loop control system. The ninth is open loop control systems do not work effectively when unpredictable disturbance and or unpredictable variation in the system components are present. So open loop control system does not work efficiently when unpredictable disturbance slash and or slash and or don't need to write here slash and or unpredictable table variation in the system components is present. So that means open loop system cannot work because when there will be, so let us copy is as it is. So other opposite will be the case in case of copy paste. Okay, so in this case what is going to happen? So in closed loop control system, let's write it like this. Okay, closed loop control system have advantages and work efficiently in presence of unpredictable disturbance and or unpredictable variation in the system are present. That means when there is an unpredictable disturbance variation in the parameters, closed loop control system can effectively respond and then can make an appropriate correction by sending a feedback signal. Rest of all, feedback signal, and then you can compare the difference. But open loop control system has not, it does not have such mechanism. So during the unpredictable disturbance, the operational capability of the open loop control system is just limited. We don't have a much flexibility in that case. So that's what is. I hope this is very simple. Comparison was there for you. So now let us move to the mathematical part of it. First of all, we'll be doing the transfer function. So first we'll go for the definition of the transfer function, then we will see analyze the transfer function. The transfer function, basically what is a transfer function? The transfer function of a linear time invariant and differential equation system is defined as the ratio of Laplace transform of output, that means response function, to the Laplace transform of input, that means driving function. Input is a driving function. Under the assumptions, we have certain assumptions that all the initial conditions are considered zero or nullified. There are no initial conditions or no initial conditions will exist. I will repeat it again. The I don't know why they are joining, what they need now. Okay, so transfer function of any type of linear time invariant and a differential equation system. How it will be defined? It will be defined as a ratio of the output, ratio of the Laplace transform of output, that is response function, to the Laplace transform of input, that is driving function. But there will be under the assumptions that no initial conditions will exist in the system. So by definition, we'll say the transfer function of linear time invariant and differential equation system is defined as the ratio of Laplace transform of output, which is what? That is a response function, to input. That's what? That's a driving function. That's a driving function under the assumption under the assumption that all initial conditions are zero. And there will be no initial conditions at all. So you have to see the response output divided by input. That is all. Take the Laplace transform of that. And that's the. So let's begin deriving. Let us begin. So we'll derive the expression for that now for any by writing a general nth order what linear time invariant differential equation. So what is that? Let's say this is a of n d of n by dt of n of what? This is c of t plus a of n minus 1 d of n minus 1 by d of t n minus 1 c of t C of t, just a second, that is C of t plus so on and so forth plus a naught of C of t, and that should be equal to bm dm. RT is input, CT is output in time domain. dt of n plus bm minus 1 dm minus 1, sorry, m minus 1 by dt m minus 1 r of t, okay, plus so on and so forth plus b naught of r of t. So let us consider this is our system. General nth order linear time invariant differential equation system is this one. Okay, where C of t is the output, that's it is the response, C of t is the output and R of t is the input. So we have considered this for the timing, for the sake of analysis. We are considering this system, C of t is. So this A, I, that means I you can put any value for 1, 2, 3, 4. AIs, that means all the A's, B's are and form of the differential equation represents the system. What does that mean? That means constants A, all these, and then B's and the differential equation. That is the complete system we have. Taking now, let's take the Laplace transform, because definition is the Laplace transform of response to driving function. Taking just a second. Taking the Laplace transform on both sides. So let's take the Laplace transform on both sides. So we already know, we have done in network complete all these things. An d by dt will represent s in time domain to s domain. So that will be Sn C of s, for your information again, plus an minus 1 s n minus 1 C of s, plus so on and so forth, plus so on and so forth. Then we have a naught of C of s and plus initial conditions. Although by formula the initial conditions should be 0, but we have to write the initial conditions terms, initial condition terms involving response, involving C of s. Whatever the terms will be involved in this case, that we have to consider. So next, this will be equal to Bm, similarly on the similar ground, Cm R of s, R will be capital R of s, plus Bm minus 1 Sm minus 1 R of s, plus so on and so forth B naught of R of s, sorry, B naught of R of s plus initial conditions terms involving RFS. Initial conditions terms involving RFS. So let us collect them together now. Or the expression can be written as, so an s raised power n plus an minus 1 s raised power n minus 1 plus so on and so forth plus a naught. These terms common, we multiply them by c of s will be equal to bm s raised power m plus bm minus 1 s raised power m minus 1. Sorry, this is bm minus 1, okay, plus so on and so forth plus b naught bracket close into r of s. So what is the definition? Now the ratio of the output Laplace transform of output divided by Laplace transform of input. So by definition, the ratio of output transform, you can write transform itself only, no need to write Laplace transform. Transform domain we normally use. Output transform C of S divided by the input transform R of S. Okay, so that will be C of S divided by R of S, which will be equal to what? So what we are doing, we are bringing the R of S here. So Bm will be on the other side itself. So that will be Bm S M plus Bm minus 1 Sm minus 1 plus so on and so forth B naught. So on the numerator, so divided by the denominator, that will be an s raised power n plus an minus 1 s raised power n minus 1 plus so on and so forth a naught bracket closed. So this is our complete expression for, I will box it. So this can be boxed. Now let us call it equation second. Okay, so add a page now here. Now this C of S, let me copy this expression. Okay, so this is copy and paste. Okay, now this C of S by R of S, we can write this as G of S also. G of S is nothing but this is a transfer function. Representation of the G of S is representation of the equal to G of S, which will be equal to. So G of S is, we can write here, we call G of S the transfer function and evaluate it with zero no initial conditions will be considered. Zero initial conditions we have studied. V naught in capacitor and inductor. What are the initial conditions? Initial voltage in the capacitor, uh, initial current in the inductor. So that are the initial conditions. Here we don't have to consider them. With zero initial conditions. Okay. So we can write C of S is equal to also R of S into G of S. So G of S is a transfer function, R of S is input. So G of S is R of S and C of S. So this is output or response, input, and this is transfer function. You have to remember this expression. Okay. So we can represent this transfer function in a block diagram also. Transfer function can be represented as a block diagram as shown. So we can represent them as a block diagram. So let me draw the block diagram. Or first I will write it. So I will write the numerator, that is Bm asterisk power m plus Bm minus 1 asterisk power m minus 1 plus so on and so forth plus B naught divided by, okay, An asterisk power n Bn, sorry, An asterisk power n An minus 1 asterisk power n minus 1 plus so on and so forth plus A naught bracket close. So let us draw this in the block diagram. This is a block. There will be input going to the block and there will be output from the block. So input is what? R of S, we know. Input to the block is R of N. This is your transfer function because formula is like that. Output. So output by input is transfer function. We have seen output. This is R of S, input is transfer function. This. So sorry. So it clarifies here that Cs by R of S is G of S, and G of S is represented by this transfer function, which itself means that C of S also response can be written as input into the transfer function. So both of the expressions you have to remember. We can box it, very important expressions. Okay. So these are the expressions. So we still have time. We'll do one numerical and then we'll. Okay, so problem number 1. Find the transfer function of the given network. Find the transfer function of the given network. Okay. Simple numerical we'll be doing today, then we'll move to from simple to complex. So what is the network we have? Network is like this. We have a resistor here. Okay. Then we have an inductor here. Then, okay. So that should be input side and that is an output side of a network. So this is your resistor and this is your inductor L. This inductor L and this is resistor R. And input voltage here is Vi and output voltage here is V naught. So we need to find transfer function. What is the definition of the transfer function? Definition is to find the ratio of the Laplace transform of response, that is output, divided by Laplace transform of input. So you have to remember that. For that, we are going to apply the KVL. So uh, this voltage will be considered as applying the KVL to the loop number 1 and loop number 2. Let us say this is 1. You can use any method. I am using KVL method for the, this is 2. So applying, you can use KCL, no problem. KVL to loop 1 or mesh 1. Better to write mesh because there is no loop within it. Mesh 1. So how you can start? Minus Vi plus, let us say, current flowing through this is I here. Let's say current flowing through this I. That will be plus Ri. Okay, that will be again plus. Now these are the two loops. So current flowing through this is I. So that will be plus L di by dt. Okay, this side, this is not a closed side, but this is a voltage we are considering that this is output. So we cannot have a volt current here. Somebody will get confused, sir, वहाँ पे current है तो we have to take minus. No, this is an open circuit here. But open circuit we can find the output current. This should be very clear fundamentals. So I can write it. Vi first can be written as R into I plus L di by dt. That should be your equation number 1. Let's set a page. Okay. Now second we can write V naught voltage is direct. There is no element connected here. So V naught voltage is directly the voltage across the inductor. So I can directly write from second V naught will be equal to, or you can simply write voltage across the inductor. No need to write this. You can write the voltage across the inductor, that is V naught will be equal to, that should be very clear, it should be L di by dt. Let's call it second. Now let's take Laplace transform of equation 1 and 2. Taking Laplace transform of equation 1 and 2. What we are going to get, we know how to take Laplace transform. Sorry, this is input here. So Vi time domain will change to S domain. R will remain as it is. I will change to IFS. And then di by dt is S. So Ls. What is the Laplace transform of inductor? Ls into IFS. Ls is for inductor. IFS. That we know already. We have done it in network. So now we don't need to repeat all those things. We have to implement them. Now V naught of S is here. Again Ls of I of S. And that is equation number 4. So what is the definition of transfer function? Transfer function here will be, that will be output, that is V naught of S, Laplace transform of output divided by input. So this is the input, we are considering the voltage. Output is Ls I of S, input is, we can take Is common from here. So that will be R plus Ls I of S. So IFS gets cancelled. So what we are going to get, V naught of S divided by Vi of S, sorry, will be equal to Ls divided by R plus Ls. So this is the response you are getting. I hope we'll conclude today. So we have done one numerical. We'll continue with these numericals now. So this is first very simple numerical where we have to find output of the Laplace transform divided by input. We have a simple use two KVL equations, and we have got this. तो मैं आज सबा मैडम से बात करता हूँ फॉर दिस क्लास, बिकॉज हमारे 10 मिनट ज़ाया होते हैं, तो वी हैव नो टाइम, बहुत सिलेबस है इसका. ओके तंजीब, यू कैन सेंड मी, ठीक है
ओके
तंजीब,
सर, कर रहा हूँ.
सेंड मी द लॉग.
हो गया सर.
Okay, you can leave, no problem.
Assalamualaikum, sir.
Just a second, I have just a second.
Sir,
Just a second, I have to stop the